So, good afternoon, ladies and gentlemen. Welcome to the second breakout session of the Geodict Innovation Conference, all about digital rock physics. Today's session is all about business cases for Geodict in the oil and gas industry. So we want to go back from the detailed session that we had yesterday and go to the big picture and have a look at different applications of Geodict for your cases and for your tasks. So I will start off with a business cases overview, and we'll hand over to my colleagues Aaron Jacob and Lobel Danicic for digital routine core analysis, upscaling, and many more topics in this scheme. And I will close with a roadmap and see if we can get open discussion running on all the features that you would like to see in Geodict. And I'm looking forward to this discussion already. So what's the business cases that we have right now in Geodict? So on this slide, I'm giving you an overview. I've split it all up into a reservoir value, production sites, the challenges with digital physics in general, and applications beyond this typical sections here. So first of all, the determination of the reservoir value would be to estimate the original oil place being at an oil feed. So that's something we do in Geodict, and we're going to go into further detail on this later. Then we have the determination of the primary and secondary recovery factor, looking at two-phase flow, primary drains, and imbibition in Geodict. We have in general, the digitalization of the routine core analysis and the special core analysis, which helps at the exploration for the reservoir value to speed up, accelerate the time from exploration to production potentially, and just to reduce time and costs required for these analyses. Going over to production sites, most prominently the production rate. It's one of the important things that you can get a grip on using Geodict at the pore scale. You're tackling formation damage by looking at filter cake formation and optimization of the drilling fluid. And finally, the formation integrity as a summary of all the mechanical computations that you have with Geodict and a grip on the stability of the rod. So with the challenges with digital rock physics, we're looking at CT scan throughput, which has also been presented yesterday by Rolf Westerteiger. We're going to look at, or not today, so in general, Geodict has a good efficiency regarding analysis time. So we've had yesterday some talks about automation, which helps to increase the productivity. And in general, we have a high performance with our Geodict solver, looking at what Andreas just introduced with this high performance computation with an 8,000 cubed sandstone rock. So efficiency is one of our philosophies. That requires to have representative images, so at a reasonable size, elementary volumes, to get representative in the sense, and that's possible with Geodict as long as you know what's the representative elementary volume for your sample and rock property under investigation. We'll go further into detail on upscaling, especially regarding the absolute permeability from core scale resolved pores towards the whole core scale, so non-resolved pores in Geodict. And we're going to have a look at what we can use unconsolidated sands in Geodict. So there's further applications like underground storage. We've heard about this already yesterday from Gordon in his talk. And also geothermal wells is something we could tackle with Geodict. Which brings me here now to back to our overview on digital rock physics. So we've had the slide before, so I'm making it fast. Kind of jumping the general goal with the reservoir and the drill cores and the imaging towards Geodict and the determination of the rock properties, from which you go to upscaling towards the scales of meters and kilometers onto the business case at your company. And we put a further focus on at this kind of interface, and that's what we do in this session today, to go from the geodetic to the business case to this kind of upscaling. And that's what we want to tackle. Okay, so first of one example. So we've talked yesterday a lot about relative permeability. So what's the business case for this property? So let's play some game here. So looking at the reservoir life cycle, at first you'll have different cycles of production rates per year, going on to a plateau in barrels per year production and moving downwards again towards the end of the reservoir lifetime. So we can calculate the annual revenue during the reservoir lifetime by a production rate estimation. So before we go further on this, we probably want to know what's the amount of oil that you can extract from the oil field, and that's something we can tackle at the pore scale with geodetics, doing a primary trench and spontaneous imbibition, which is giving us an idea of how much oil we can extract via primary recovery. So assuming we have a reservoir of 50 million barrels, original oil in place, and a recovery factor, maybe with this primary recovery of 0.2, this might sum up to a total revenue of like $800 million. So that's the numbers here for this estimate. Going further to secondary recovery in geodetic, we can not only compute a spontaneous imbibition, but we can add onto this the forced imbibition part of the imbibition to mimic water flooding. So with the secondary recovery, more oil can be produced. Let's assume we can increase the recovery factor up to 0.7, so we can expect 70% of our 50 million barrels of oil in the oil field. So let's assume this, which is increasing our total revenue of oil from the reservoir by $2 billion in this sense. And that's basically the numbers behind what we do here. So going further to the reservoir performance idea, so you can predict the absolute permeability and the relative permeability to understand the performance of your reservoir. You get a grip, what's your well production rate per day or per year, what's your annual revenue per well. Or you can get an understanding of these values. And now going back to the reservoir life cycle, that's something you can compute by having the relative permeability curves in geodict. Can get a good understanding on these things. And so that's the mind game for the business cases that we want to play today. So next up, I will give words to Arnold Jacob on the routine core analysis.
So thank you very much, Christian, for this overview of the business cases we are talking about today. I would like to start off with a digital version of the routine core analysis you usually do in the lab. So as Christian was mentioning before, and as we were also talking about yesterday, the first requirement you have to fulfill is that you need a core plug from your reservoir, which is representative for your reservoir facies which you want to analyze in that case. Then you will need an imaging device where you can get the images from to obtain the digital representation of your structure. And based on that digital representation of that structure, you can then start by segmenting your structure into different phases. So you want to assign the gray values you get from your imaging methods to different material properties. For example, material properties for quartz, but also feldspar, calcite, cements, or whatever. And based on these segmentation, you can then run the simulations to predict absolute permeability, relative permeability, and so on. And last but not least, you can then use that information you've got from your routine core analysis to put that data into your reservoir simulator to put it on the kilometer scale instead of only having a look at the centimeter or even micrometer scale. If you run these simulations digitally, you save costs and time, and it also allows you to use the sample for not only one time. Let's say you have an MICP. You may destroy or even modify the pore geometry by pushing the mercury inside of your structure. And since micro CT imaging is non-destructive, that is a big advantage of the digital methods here. As we have covered the image import, image processing, and image segmentation beforehand, I would like to give you an overview of the image analysis and generation, but also property predictions today, which is namely determining porosity, pore size distribution, percolation path, grain pore and fracture identification, but also flow properties and all the others you can determine by using our prediction modules. Today, I would like to cover within the routine core analysis workflow, the absolute permeability only for today. But I will also talk about upscaling these results to larger scales where you need then Darcy flow computations and an upscaling of the flow algorithm. As Christian was also mentioning yesterday, we're having advanced filters and also AI-based image enhancement algorithms that you can apply to your digital images, which will help you enhance the image throughput and also enhance the image quality by itself. That cannot only be filtering, like filtering the noise you will get usually from micro-CT devices, but that can also be the removal of ring artifacts or removal of gradients that came from cone beam geometries, but also flickering and curtaining effects from FIB-SEM measurements. As Christian was also showing yesterday, we are having different algorithms or AI-based algorithms like random forest and boosted tree, but also deep learning algorithms like the UNet to differentiate between the different phases that are present in your gray value images. And you can then use this information you have to populate the model by different training regions to feed the training data for the algorithm, and then you are enabled to obtain a very good segmentation for your structure. First of all, in a digital routine core analysis workflow, you want to characterize the porous media. So you can have sandstones, carbonate shales, and so on. And as you want to know how much hydrocarbons you have inside of your reservoir, you want to analyze the pore space, the size distribution of the pore space. So maybe a porosimetry is a good choice here. The connected porosity, unconnected porosity, the size distribution of the pores, and so on. But it is also possible in GeoTIC to identify the individual pores. So you can put like an index on each of the pores and count each index of these pores to be able to obtain the total number of pores. And based on this information, you can then even use that structure to generate your own statistical twin, like it was shown before, where we showed the approach how to upscale from 2D to 3D. For hydrocarbons, it is necessary to have the total porosity and also the accessible porosity, because if you have hydrocarbons within your reservoir, but you cannot reach them because they are non-accessible, they just stay there forever. So you want to have a differentiation between the accessible porosity that has a connection to the rims of the sample, and you want to know which part of the porosity is non-accessible. And that can be easily done by geometrical analysis within the GeoTIC software. You also want to know how large the diameters of the pore throats are, which helps you then determine how good the flow can pass through this pore space. That can be not only done for the largest percolation path, but also for, let's say, 10 or 5 largest percolation paths that are present in the structure. That also helps you to illustrate heterogeneity in your structure. That means if you have only one large, let's say, fracture within the rock, mainly the flow will pass through that fracture if it tries to leave the structure, or if you want to extract it from that kind of structure. You could also identify not only the individual pores, but you can also run a certain kind of algorithm on the grains, where you can also put index images for each of the grains, which means that each of these grains has a different numbering. And that gives you a distribution of different parameters these grains have. That could be sphericities, but also surface to volume ratios, volume probability, and so on and so on. So in principle, every geometrical parameter that you can think of. I was also talking about yesterday about fracture analysis, which we can do within GeoDict. So I will only have a short glance at that slide here, which gives you also the orientation of the fracture and also the total volume that a fracture has related to the total pore volume. When doing a digital routine core analysis, you also want to have the absolute permeability, which is also very important to know how much hydrocarbons you can get out of your rock. And especially in that case, our simulations are extremely fast and efficient. For that case, we have run the simulation of 1,000 or 900 to 900 to 570 voxels on the Gildehauser sandstone, and that took only about 15 minutes on a 16-core machine to predict the permeability for that kind of sample. You can also run that fluid flow computation on larger and encased structure. Lobel was yesterday showing how to apply that shrink sleeve to the structure, and also Andrej had some very important questions about that, how to consider the correct permeability in that case, because you have to account for the first slice and also for the last slice. They have to have the same share as to be able to compute the right permeability. And visualized here, you can see the fluid flow velocity field on the left-hand side and the pressure drop visualized on the right-hand side. It is possible to do a complete routine core analysis in GeoDict by only one click if you would like to use the digital routine core analysis app. So in principle, the workflow looks as follows. You load your structure, which is in that case the Gildehauser sandstone again. You go to the Geo app section, open the digital routine core analysis Geo app, and then you can check or uncheck the parameters you want to determine within your digital routine core analysis Geo app. That could be porosity, porosimetry, the identification of individual pores, but also the surface area, the material statistics. So that means if you have heterogeneity of solid volume fractions or so, you would see them in the material statistic analysis. The percolation path we have already talked about, and the absolute permeability. And the last two parameters can also be direction dependent. So the permeability could be different based on from which side you want to have your fluid injected for computing absolute permeability. So you can choose in the GeoDict Geo app from which side you want to have your fluid invading the structure. Then you run that by just clicking OK and run, and then it will sequentially execute all these different parameter simulations that are checked on that left-hand side. And that will give you a variety of different results based on the checkboxes here you checked. So in that case, I have displayed the porosity visualization, the absolute permeability visualization, percolation path, and the material statistics as plot. And as you can see, you have an oscillation of the quartz content and also the pore content, and they are more or less in the same range of oscillation with the same amplitude. And that will also give you a nice PowerPoint report. So that is not only about giving you the results, but also about automated reporting. So if you run that app, a PowerPoint report will automatically be created with all the visualization included already. So in that case, you can see that there are about like 10 or even 11 slides, while each slide gives you a short or brief information about the parameter you checked here on the left-hand side. So in that case here, you see the slide where the absolute permeability flow field was computed and gives you in the report the number for the permeability. As next topic, I would like to talk about how to upscale your plug to core scans. As Lobel yesterday was mentioning, you're usually having the trade-off between field of view and resolution. We have highly advanced methods to resolve structures that are on a nanometer scale. Like in that case, I think it is a shale reservoir here. But the problem is that the field of view is then not large enough to be representative for that whole type of rock. And that means that you have to upscale that information somehow to the larger scale, where also other very important properties are displayed on, for example, here on that mini plug scale. And if you go even further, you have not even your pores resolved correctly anymore. And you also do not see the grains anymore. So that means on the right-hand side, you can only work with, we call them porous voxels, where you assign different permeabilities to different gray value ranges. So in principle, you are following the workflow that you want to upscale the highest degrees of resolution or information you will have from the lowest scale, from a nanometer scale, to the largest field of view here on the right-hand side. And we're having different solvers, for example, for that microporous domain, where the pores are still resolved. We are using usually the Stokes solver. And in case of microporous regions, you can then add the Brinkmann term to that computation, which will then allow you to also assign different permeability values to these grayish or these unresolved porosity that also contributes to the permeability. So it is not sufficient to only compute the pore space you can see, but it is also very important to include the parts of permeability that are hidden within or by the resolution you have. I think Christian already showed one of these samples yesterday. What you can see here is an unresolved structure where you have different solid materials, but also different porous materials. And these porous materials have a certain kind of permeability. And you can now go the way to say, okay, I have another method like FibSEM. I determine the permeability for this porous matrix material. And then you can go the way that you assign this permeability to these dark grayish areas here in the scan where you have a larger field of view. And based on this local permeability, then you can compute also the whole permeability for the larger field of view as well. Because then macroscopic effects like isolated larger pores or even areas where the solid minerals are more dominant play a more important role than on the nanometer scale. And for that, we have a dedicated solver that is called the Darsk solver. That is much faster than the Stokes solver that can also be used for that case, but that was usually built for resolved pore structures. So the Stokes solver is extremely fast for resolved cases where you do not have too much of these porous permeability available, while the Darcy solver is for the cases where you have like only unresolved porous materials available. And as you can see, if you're doing a benchmark, both solvers will give you the same permeability for the same structures, but the runtime will differ largely. So Darcy solver was built for that, only takes half an hour, while the Stokes solver with the Brinkmann term added takes 81 hours here. Yesterday, I would also like to talk about the quantitative seismic interpretation, but due to some time issues, I wasn't able to talk about it yesterday, but I will do it today for you. So in principle, what you want to do is you want to increase the understanding of your reservoir or do reservoir monitoring during CO2 injection or during the extraction of hydrocarbons. And you can also derive a fluid saturation distribution from seismic monitoring as well. And that helps you to increase the confidence for reservoir management decisions and optimizations. And of course, it helps you to estimate the risk that comes with CO2 injection, for example. The way we follow in GeoDict is that you first have to have a representative digital rock volume that you want to analyze. Then we compute the porosity, fluid saturation, and bulk density for that volume. This is simple geometrical analysis. And then where the solver come in, you want to have this direction, fluid, and saturation dependent stiffness for that part of rock you want to analyze. And based on these parameters you get from that simulation, you can then derive the P and S wave velocity, but also the compressional slowness, acoustic impedance. So in general, the seismic parameters for that structure. As a theoretical background, I would like to show you the equations we're using for that approach, which would be the equilibrium equation and the kinematic equation to compute effective stiffness. Computing porosity is rather simple, and also computing the bulk density. And based on the bulk modulus we obtain from these effective stiffness computation, we are then enabled to compute the P and S wave velocity, as well as the acoustic impedance and the compressional slowness for this type of rock. So what we get from only these images of the rock and the material distribution within that scan, we obtain the fluid saturation distribution, the gas oil water content or CO2 water content, the P and S wave velocity, the compressional shear slowness, the porosity, the stiffness, and the acoustic impedance and bulk, fluid, and solid density. Thank you very much.
Thank you, Arne. Greetings, ladies and gentlemen. So now I'll continue with the next topic of today's session, and that's the estimation of original oil in place. So building upon the information that Arne and Christian have shown in the previous sessions, I would like to continue now with the next idea that you could use geodict for and gain value out of the geodict computations that you may so far have not been thinking of how to apply geodict. First, I would like to start with describing in short and simple terms what original oil in place is. So those are the quantities of oil that you initially find in the reservoir when you discover it. And just by going through simple play or game with numbers, if the reservoir in place would have 50 million stock tank of barrels of oil, and for instance, if you would have 1 plus minus % of error in OIP prediction at a price level of oil of $80 per barrel, that would make a difference in $40 million plus minus. So when you still apply then the recovery factor, that could be the millions of dollars of the value you either mispredict or don't realize. So one additional note on original oil in place is that it's in the end of the or in the beginning of the field's life cycle, one of the most important factors that will govern the field development decision making. So here we would like to present you with the fast workflow in geodict that helps you predict some of the properties that you need in calculating the original oil in place. Now I would focus on the reservoir itself and also go through what original oil in place consists of. So in the main part, it's the reservoir's bulk volume. That's usually the work and estimations from seismics and other large-scale interpretations. Then there's the porosity that's governing the amount of original oil in place, as well as the oil saturation. Finally, there's the oil formation factor that's transferring or conversion from the reservoir conditions up to the surface conditions of oil volume. And as such, 2 out of how many? 4 in total parameters, so porosity and oil saturation, you can compute in geodict, and they have a considerable effect on overall oil quantities present. As such, I wanted here to highlight what's the importance of porosity, as I call it first part of the equation, on the amounts of oil and what of the all amounts you could actually produce. So to give you an idea, what this slide in one or the another form you have already seen in the porosity prediction and characterization talks, for instance, from Arne. And here I would like to highlight that, for instance, accessible pores are the ones that would contribute to the flow of oil, as well as the both accessible pores, closed pores, and dead-end pores contribute to total fluid volumes. However, in that sense, accessible pores are the ones you would consider in getting that oil out. Now, the second part of the equation, I say it's the oil saturation. And as such, oil saturation is very important. And back from 1942 and Gus Archie's development of the Archie's laws, we can connect the resistivity measured of rock sample with the oil saturation in place, oil and water saturation in place. And that is one of the computations that I would like to now show in GeoDict for the obtaining of Archie's parameters that you can later use to calibrate your resistivity logs in the wellbores. So this, if you have been with us yesterday, I also went through the approach how experiments in the laboratory setups go and how we do it in the digital environment as well. So to predict the Archie's exponents. Experiments start with the fully water saturated rock sample that is then being drained by injecting oil and measuring the resistivity at different saturation points. Then by plotting the resistivity as expressed through resistivity index at different water saturations, you're able to determine the M and N exponents, and later you use them in calibration of your Archie's equation and of your resistivity logs. So just now as a wrap up, to determine the original oil in place, some of the quantities that you can compute in GeoDict include porosity and Archie's exponents, and that you can do at the pore scale. Then by, for instance, if you want to get the information on the, and reduce the uncertainty on the larger scale, on the whole core and even formation level, you can do the multitude of core plugs experiment in digital environment and average the results. Finally, those results you can utilize to calibrate your resistivity logs and finally come up with the original oil in place volumes. So this is for the first session of today. So if there are any questions, I'll be willing to ask. Good. Then we would like to, I'd like to continue with the next topic. So also to give you an idea of what GeoDict is capable of and what you may find value and start using GeoDict for. That is the drilling fluid optimization, or what are the benefits of. So I would first and short want to explain what the drilling fluid or MUD is and what are the importances of its optimization and why to do it digitally. So as it's written, MUD is one of the key parts of the drilling process in oil and gas industry and also for other applications when there's the drilling. And MUD cleans the wellbore, taking out the cuttings and also at the same time giving the stabilization of pressure on the wellbore walls, so assuring the stability. During this flow, there's the tons of particles circulating that could cause the formation damage. And that's quite often also occurring when the particles invade the formation and go, when the mud filter invades and moves deeper into the formation. And that is one of the main reasons why you would want to optimize the mud itself. So to minimize the potential plugging of your reservoir formation, and also reducing other interactions that could occur, such as reactions with water, and also stickiness of mud cake on the wellbore wall that in the end they require more of the well simulations in that case. So why to do it digitally? When we were thinking of this topic, we wanted to consider some of the main benefits of digital experimentation, so to call it. And number one is definitely that it's non-destructive, and you can do it many, many times, so not wasting your core sample. The setup itself is quite simple and quick in comparison with, for instance, experimental setups. And also you can get the additional insight that is not readily available in the classical approach of flooding your core. So that's just a brief overview on the sheer amount of ideas that you could think of for utilization of such feature digitally. So now, just in short, I would like to say how the and show the scales of how the mud cake is formed on the reservoir wall, and how the scale we can investigate in geodict changes. So, for instance, what we focus on is the millimeter to micrometer scale present in the right. And by doing simulations in geodict, what you can see is how the pore clogging happens when the particles are invading, and how, due to the different interactions, they stop their movement, so to say, and they clog the pores. Here is just the 2D slice, and for instance, in the middle, for the more clarified situation, and in the middle you can see the 3D representation. And now, so what are the exact effects of such clogging by the particles invading? So here I wanted to highlight the example what happens with velocity field prior and post the simulated mud invasion with particles, and how the flow field changes its both the streamlines and the values. So what this affects, I highlighted on the right part. With particle invasions, you get the effect on permeability, and that's one of the key aspects you want to consider when optimizing your drilling fluid, so that there is as small as possible effect on permeability reduction. Also, that comes with the invasion depth, or what's the scale of permeability reduction along the distance from the wellbore walls, so to call it. And also, what's the effect of different particle sizes? So, for instance, if you would use the different composition of particles, different particle size distribution, how that would affect the permeability reduction, for instance. And now, wrapping it up all together, we would like to also show here that with geodict you could simulate the mud cake formation, or the invasion of particles into your 3D rock, and then compute the properties of the mud cake itself, how it affects further invasion of particles into the rock example, and how it, for instance, prevents further damage. Then also see for different particle size distributions, how they affect the creation of mud cake and how they affect the permeability or the depth of invasion. And finally, we want to also say that this, for instance, could be done for not just the one of the lines of the or one of the formation segments of drilling, rather during the whole across the whole part of the corings you have obtained during the drilling process. And as such, to get the best composition of drilling fluid based on the particle sizes. Thank you.
So I would like to continue with CO2 trapping potential. And first over the question, so why are we doing CO2 sequestration? So this is probably a whole question to discuss, so I will make it simple here. So we put it here as a business requirement, but still I would like to play the game. What's the potential revenue that we get from CO2 storage? So I'm looking here at a sample reservoir at 50 megapascal and 50 degrees Celsius to consider the supercritical CO2 density for this. Calculations, which is basically meaning that we get more or less $10 per barrel of CO2 storage in the supercritical state. So why are we saying this $10 here? So based on the Inflation Reduction Act 2022 in the US, you'll get for permanent storage of CO2 an amount of $85 per ton of CO2 stored permanently. And also even more if you have applied direct air capture as a method to capture the CO2 from the atmosphere, accounting to $200 of storage of per ton CO2. So these are the numbers on this one. I will go further in the next slides. So where are we looking at? We're looking first at the reservoir management. So we want to estimate the total mass of CO2 that you can inject and store permanently. So this is quite a challenge. And onto this, you must or will want to calculate the total costs for the injection side, but also the revenue. That's alongside of this. So there's also the topic of risk management to assess the reservoir safety, both from a reservoir scale perspective, but also from challenges at the wellbore region. Okay, for the injection site management, the challenge would be to optimize the injection rate for the supercritical CO2 in order to optimize the storage of CO2. And here you want to avoid the issues in the near wellbore region, which is like, for example, the drying zone, which would be unfortunate. Okay, let's have a look at the scales. So we have our motivation to do CO2 storage as a business requirement with potential future profits. So again, our reservoir with a storage potential of 50 million barrel would account, given the CO2 density here, to $500 million of revenue, not considering the costs alongside of the injection. So what you can do now to get a better understanding is you can do a lab scale CO2 flooding experiment in your course. However, with the lab setups, you are limited to short time scales, so maybe hours or days. Kind of limits the setups that you can do experimentally. So the chances here to go digital way. So at the geodetic scale, so micron resolution, you may compute the effect of CO2 injection into the rock. So, I mean, you can look at capillary trapping, water-rock interactions, so looking at geochemistry here, And along to this, you might have mineral precipitation and dissolution, so the geometry will change, resulting in a changing porosity, absolute, effective, and relative permeability, even changing mechanical properties. And all this can be computed based on the rock changes that you predict for the given setup. So having all of these values at the pore scale, you need some kind of upscaling. So maybe a reservoir simulator also capable of geochemical calculations, or some other layer, for example, to monitoring. Okay, so let's have a look what we can calculate in geodetic right now to predict the storage of carbon dioxide per formation rock, or per formation in general. So we can compute CO2 capillary trapping. So basically, we compute an injection of supercritical CO2 in brine saturated rocks and obtain a residual saturation. Now, not considering solubility questions here for this one. So we can compute mineral trapping, meaning we simulate the injection of a CO2 brine, so a CO2 saturated brine, and we have a look at what mineral dissolution and precipitation reactions are we triggering with that CO2 saturated brine. So maybe we get precipitation of carbon-bearing minerals depending on our formation, fluid, pressure, temperature, salinity, and all of the values that we can assign to a computation here digitally. And finally, we have the question of CO2 solubility trapping. So solubility trapping is probably something about soluble or solution rates. But speaking more in general, we can calculate an equilibrium of supercritical CO2, or one can calculate using a geochemical calculator. So we can calculate an equilibrium of supercritical CO2 with a formation fluid. And even for this, consider a residual brine saturation. So you look how much residual brine do I have in my reservoir rock, having done a capillary trapping simulation, and how much of the supercritical CO2 may dissolve into the remaining brine in my rock. So that's something we can investigate onto an equilibrium state. Okay, so if you've computed rock properties prior to entering CO2 injection, so if you have computed mineral dissolution or precipitation, you can compute rock properties prior to and during the CO2 injection, meaning we are changing the geometry. So we can also compute the change in porosity and the transport properties, but also the mechanical properties and whatever else you want to look at with GeoDict. Okay. To get an understanding, we might be aware of the time frames of CO2 sequestration. So there's different trapping mechanisms when we inject CO2 to a reservoir, and these occur on different time scales. And each of them requires a dedicated approach. Okay, let's have a look here. So we have structural trapping at first, which is mostly a reservoir question or reservoir scale question, looking at how is the sealing capacity of my reservoir. Are there any faults that I need to consider? What's the sealing capacity of my cap rock? Questions like this. And then we go to capillary trapping, just mentioned earlier, going at the time scale from, again, that you can see here on the x-axis along. And finally, after capillary trapping, as I just mentioned earlier, you can have a look at solubility trapping, which happens a little later from the time scales itself, and has some questions on the rates, of course. And finally, mineral trapping, which is said to occur at a much longer time scale, which is, of course, the most preferred way of permanent CO2 storage in the underground. Okay, so at all times, of course, the reservoir safety is one of the field scale issues initially, but on the long term, of course, requires digital tools. It is a time scale issue. Okay. Let's have a look at capillary and solubility trapping for CO2. So at first, we can do supercritical CO2 drainage. So we inject supercritical O2 into a brine saturated rock as a setup. So we're doing a forced drainage, displacing the formation brine. So we can compute that with geodic onboard tools and get an understanding on the capillary pressure curve and the residual. So having had a look at this, you probably want to have a look at solubility trapping. So you can employ geochemical equilibrium thermodynamics or a geochemical calculator that does this. And have a look, well, how much of the supercritical CO2 will, with time, dissolve into the brine as aqueous CO2. So what can be done is you can calculate the CO2 concentration that equilibrates into the residual brine, looking at the residual brine saturation just from our SeCO2 drainage. So that's something that can be done, yeah, more or less with this geochemical equilibrium thermodynamics. And what you might probably also want to consider in the future is CO2 dissolution rates, which I'm not aware of, like rates at reservoir conditions. So high temperature, high pressure, high salinity, and a given formation fluid composition. Okay, having had a look at all of these values, you want to probably do some upscaling on this. Getting an idea on how much of the aqueous CO2 can be trapped in the residual brine, how much in gigatons probably of the supercritical CO2 may be trapped in the pore space, and how many millions of dollars might this be for permanent CO2 storage in the reservoir. So let's have a first look here at what the geodic workflow is for computing water rock interactions. So we typically start off with an input geometry, so which is here a Grossmont carbonate rock from a Canadian formation from the Andre et al. Publication of 2013. Using this carbonate rock here, we simulate the flow, so the velocity field in this rock. And as a sequential workflow, subsequently we compute particle transport based on the advection field that we have just computed, and also the diffusion of the particles, so molecular diffusion. Okay, so we've got advection and diffusion, and now we are adding on to this chemical transport, computing based on the particle transport paths, the transport of our injected reactants into our structure or into the pore space, through the pore space. Okay, so this will probably trigger reactions. So we have a carbonate, we're injecting CO2, saturated brine, or any kind of acid that will trigger dissolution reactions that can be tracked in geodict. You can see in this animation. So here in this animation, they are tracked as red marked voxels where the dissolution will occur. In this case, for the given acid setup and fluid composition, temperature and pressure, so just for the setup. And of course, the injection velocity. Okay, what you get out of geodic computing such a setup is a whole set of post-processing parameters. You will get a porosity permeability plot, a gradient for the porosity from the inlet to the outlet, which is typical for dissolution patterns. Get a grip on the porosity development, the reaction rate, Damköhler number, Peclet number. So all the typical parameters that are known from publications on this topic. And now let's have a look at upscaling of the mineral dissolution for CO2 sequestration. So what does it provide us with, or what can we do to upscale it to larger scales? Okay, so at the geodic scale, at the pore scale, we'll simulate the injection and compute mineral dissolution and precipitation based on the setup that we have. For this, we get continuously changing rock properties such as porosity permeability, or we can compute additional properties such as relative permeability and effective permeability for different states of the geometry during continuous dissolution and precipitation reactions, while the geometry is continuously changed. Then the next step would be to have a look. So this is the suggested workflow. Next step would be here to have a look at pore scale seismics. So Arno already introduced what we can do in this respect. So we compute primary and secondary wave velocities in geodict. We calculate the bulk densities and get the primary and secondary wave velocity by computing the effective stiffness for the different or for the rock at the different time steps or different porosity steps during or in a water rock interaction setup. Okay, so you get different density, velocity plots, for example, for the different states of our reactive transport simulation. And now we can have a look at upscaling. So how can we relate this? So we can relate this, for example, to seismic monitoring. So if you have continuous seismic monitoring at a CO2 injection site, you will see differences in your seismics depending on the injected supercritical CO2, which will induce differences in the seismic image, but also changes in the rock structure will have an effect and will be seen during the monitoring. And these changes in the velocities in the monitoring can be correlated backwards again to the Digirock physics simulations in order to give you an idea of what's going on in the reservoir during CO2 injection. So it helps you to understand reservoir development. So how does my rock look if I get these and these changes in the seismic monitoring? And along to this, you can get an understanding on how your rock properties are changing, how the permeability changes, but also relative permeability changes alongside with this. So you can predict the effect on the storage of CO2, on the amount of storage, and get an understanding in general on the reservoir development during CO2 injection using this kind of upscaling approach. So this workflow is not yet in a production, but it is under evaluation and on its way. Okay, next topic would be the increased scan throughput. You've heard already something on this in yesterday's talk about artificial intelligence in geodetics. So probably trying to keep this short. Just have a look at why are we doing this? Why do we want to increase the scan throughput? So scanning times, as we often hear, are a bottleneck for Digirock physics. So we want to tackle this now with this approach by digitalizing 80% of the exposure time. How we want to do this? So we want to train neural networks based on ground truth data and apply these trained models onto short exposure time scans in order to reconstruct the ground truth. So high quality images. So what would be the benefit to do this? So let's make some assumptions here. We have a core lab with 100 cores per year. With per core, we have 10 hours of MicroST scanning time, summing up to 1,000 hours annual lab time. Just one assumption. So what would be a benefit? One potential benefit would be we can reduce our OPEX costs, operational expenses, by saving 80% of our lab time and just thus saving 800 hours per year, if we can sum this up like that. Which could be worse. We'll put some number here, like maybe $200,000. Just one number. Or we can also just accelerate the digitalization process. So we can reduce the lab needs per core and thus speed up exploration and production. So if you not yet having the time to image all the samples that you're getting at peak times, can just reduce the needs per core and thus speed up potentially exploration and production. So you can speed up the time from getting the cores to getting values for the cores, and thus maybe even speed up the time to production, which can generate quite high numbers of revenue per year if you can speed up the entire process. So accelerating the digitalization has its opportunities in that. Okay, how's it working? I will make sure I make this short. So we have ground truth data of short and long exposure time scans. We're gonna train a neural network on them. The sample pairs, probably of each representative or each formation and rock type that we want to have it trained on or for. And having a trained model, we can apply it on any short resolution scan that's within the samples that we have trained our model for within the sample range. And we can reconstruct the ground truth based on this. So the validation of this approach is ongoing work. Let's have some visual comparison right now with a goal to have short exposure times being sufficient in core labs to choose the time required for throughput. Okay, now here we have a high quality scan on the left-hand side, long scanning time as a minors, but a minor noise and high image quality. In contrast, the short scanning time will have a noisy image and not as good image quality as a long exposure time scan. So if we now apply our trained model on the short exposure time, we can reconstruct the ground truth, having trained the model on such kind of rocks, and get from the low quality scan just with 20% of the scanning time or even less, reconstruct the high quality image, which is at least as good as the high quality scan. It requires a lot of more time in the lab. So it's a trade-off between the lab time and the digital approach, which can be automated to a high degree. Okay, just one more full screen thing here. Here on the left-hand side, you see a low quality scan of this rock, a high quality in the center, and on the right-hand side, the low quality image with the applied trained model. And you can see on this one, at least, that there's even less noise in the AI improved image quality. So the quality seems to be fairly better than even the high quality scan. So it has its applications. Okay. So much for the agenda. So there's still roadmap and open discussion. But before I go on to this, I would like to check unconsolidated sense. So if you have a sand package, unconsolidated sense, I want to get some properties for these sense. It's a challenge, both in the lab or as a digital approach. So what you can do digitally is you can get a grain size distribution, model a rock, or grain size distribution to model a rock, and group some property on it. But it's not that simple. So to get a more validated workflow on this, so we've tried something out in the past to work with pairs of grain size distribution and the property to predict. So having some ground truth data. So having some probability prediction from the lab. So for example, for a sandstone rock that's been crushed, to get a grain size distribution measured by a laser technology. And go further with this, apply a machine learning workflow to get a grip on how do we have to set up the generation of a digital rock in order to meet our properties to predict. So in detail, it's about getting an understanding of what resolution do I need depending on the grain size distribution that I'm looking at. So and depending on the grain size distribution, maybe of 3 orders of magnitude, you will need a different resolution to get a grip on the most important resolution or features. So there's something to consider in this. We have worked on this and we had pretty good results. We reconstructed the ground truth by using new grain size distributions, applying our machine workflow to understand what voxel resolution we need, what setup we need. We produced digital rocks, 1000 cubed out of this. One example would be such a rock. You can see there's large grains in there and there's small grains in this rock. And we could recompute the permeability that the rock has seen in a lab without having used this rock for machine learning training. Let's call it like this. So we can reconstruct the rock property from a grain size distribution and a given porosity by having trained our machine learning workflow for this one. So this works out quite nice, and it can also be applied to cloud computing, so you can predict rock properties for unconsolidated sands with this kind of workflow, and just advance to further steps towards production with these parameters. Okay, now, as promised, the development roadmap. So on our short-term roadmap for this and the upcoming year, we have effective capillary pressure and relative permeability on medical CTs, so on the Darcy scale. In other words, a two-phase Darcy solver for the unresolved system. As the next thing, we have the computation of PNS wave velocities. We've presented that we solved it, but we have not yet implemented it. So it's basically on our roadmap here. So going to be probably implemented in one of the next upcoming server specs for GeoDict. Finally, the computation of 3D rock properties from 2D thin sections. As we've introduced it earlier these 2 days, we have our Geo app available that's doing something, but it's not yet working for all of the different challenging types of applications. So yeah, please help us and provide us with feedback on this one. Furthermore, we have advances in the LIR solver for geomechanics planned, as just presented during the Q&A by Arne. So we are working on this to get the PNS waves improved by frequency consideration, for example. I also have this on our midterm roadmap, so meaning 2025 or even later. So there's increased capabilities dedicated to unconventionals on our agenda. The improvements for CO2 train potential. So we want to work on this further in the future as well. Advance our solver for geomechanics. So just as I've stated, the compressible fluids and frequency dependency. So we will see what we can do in a short-term scale, and we have more advances for these things on our midterm roadmap. So we already have something for compressible fluids. So it's just advances onto this. So please don't take me wrong. Then we have improvements for AI on our agenda with GeoDict as a general platform for artificial intelligence and machine learning applications. So for applications all around image processing, segmentation, there we already have something, but also could be applied to grain identification and prediction of rock properties based on these kind of workflows. So it's all about imagination, what you can do. It's probably possible in the future. And also we have advances dedicated to cuttings analysis on our roadmap here. I would pretty much love to hear what your need and priorities are. So we basically can arrange to some certain degree our roadmaps. We always listen to our users, what their need is, what their current use cases are, what they need GeoDict for. So please let us know if there's anything on your mind and agenda.